So I want to give you an example of how such a misusage of a pseudo-random number generator can look. This was a bug that I found a while ago in a product. So we generate API keys, and we do so by using random string utils from Apache Commons library. The first parameter is the length of the string we want to generate, and the second parameter is a string. So what random string utils.random does it takes random characters out of this string and appends them to one another. Change the color. So we have 100 character string that looks random because random characters out of this supplied string were chosen. So how does that work? Well, internally, random string utils uses the Java random number generator, which is an LCG, linear congruence generator, 48 bits of state. And within the random string utils, it uses this, call this .next 31 bits. So it uses the LCG to get 31 bits. Now imagine we are a customer, we get one API key, but of course we want to calculate all API keys of the other customers as well. So what we can do is, well, let's see, we get characters. If we issue a API key, if we request one, we get a 100 character long API key, something like this. Oh, it's MRG, and because we know they use random string utils, we know that the output of the random number generator was 13, 44, and so on and so forth. Well, it takes these 31 random bits out of the LCG, but then it does them modulo 62. Because our supplied string is only 62 characters long. So it takes the 31 random bits modulo 62 and then chooses, based on the output of the random number generator, modulo 62, which character to use. So it does gets 31 random bits, then it takes the modulo 62, and this output here is the offset at which it will take a character. So this value, 31 random bits modulo 62, the first output was 13. We can see that in our API key that we received. It starts with an M, so 13. Well, the Java LCG is 48 bits big. That's too large. We don't want to brute force that. That's not fun. Well, how can we still get a full API key and, of course, the API keys of the other people? Well, let's look at the LCG again. Well, it's actually a special case of an LCG. As you can see here, it doesn't use the modulo operation, it uses a logical AND. That is because LCG uses mod 2 to the power of 48. As a special case, it only uses the lowest 48 bits. This number here is 2 to the power of 48 minus 1. So the LCG takes a state, multiplies it with the multiplier, adds the offset, and then just only takes the lowest 48 bits of the result. That's relevant because in this case only lower bits of the state affect higher bits. So every bit after multiplication might affect all other bits higher than it, but no bit ever affects a bit lower than it, right? Because we just multiply and add and then cut off the number at 48 bits, so we don't wrap around the modulus, let's say, we just cut off the number. That's one observation. The other observation is, since the call is rand 31, it's 31 bits here, so it shifts the internal state by 17 bits to the right and then uses the highest 31 bits of the LCG as output. So the highest 31 bits is here. If this is 31 bits, 17 bits, the highest 31 bits, these here, are taken modulo 62, and then they, with this number resulting, we get the offset of the character that we use for the API key. Another observation is the modulus is 62, because our original string here is 62 characters long, right? So if we take an even number, modulo 62, we get an even number. If we take an odd number, modulo 62, we get an odd number. So actually, with every character in our API key, we leak 1 bit. So with 13, we know the output of the random function of the 31 bits modulo 62 was odd, because we got an odd number, 13, the 13th character, the M. With 44 we know the output was even, so we can leak 1 bit per character of a state. So we know the first state was the 31 upper bits were odd, the second state the upper 31 bits were even, and so on and so forth. So what we can do is we can employ a kind of meet in the middle attack. So we have this bit, the 18th bit, that leaks directly per state. So with every character of an API key that we issued, we get 1 bit, this bit here, because we know if the highest 31 bits are even or odd as a number. So what we can do is just brute force through all possible 17-bit states in the internal states 0 as 1, Actually, we just only need S0, sorry. Brute force through all bits and then see which 17 bits in the beginning led to these patterns of ones, like odd, of zeros, even, and so on and so forth, with all the characters of our personal API key. This works because this bit here is only affected by bits lower than it, so by lower 17 bits. And these 30 bits are only affected by bits lower than them. This is the special case of an LCG. So what we can do is we leak 1 bit per API character of our API key. So first bit is 1, so in the first state this bit here in the middle is 1. In the second state this bit here is 0, and we go through all possible 17 bits combinations. If we go through all possible 16-bit combinations, as you know, that's 6, 5, 5, 3, 7, 3, 6, sorry. So we have to go through roughly 65,000 possibilities, which is easy, and then check if the output afterwards of these would be this pattern of ones and zeros. And once we have found that, we go through all possible 30 bits combinations, so 30 bits. It's around 500 million. Sorry, it's late. I'm really sorry. It's 500 million, sorry. So we go through all possible 30 bits and then check if actually this sequence of numbers would come out, like 13 for the M, 44 for the R, and so on and so forth. And then we just combine the correct 17 bits with the correct known bits that were directly leaked with the correct upper bits, and we have found our 48-bit internal state of the LCG. And then we can, of course, just run the LCG backwards and calculate all API keys previously generated by other customers. These are not unique. There might pop out a couple of candidates for the internal state, but that doesn't matter since we can just test through a couple of them. So this was a real vulnerability that I found, and it shows you that it is never okay to use pseudo-random number generators for security critical purposes.